So valence shell electron pair repulsion theory is this lone pair, lone pair, lone pair, bond pair, bond pair, bond pair repulsion. So the electron domains repel each other. They don't like to be near each other. Electrons of the same spin will repel each other. So the space between electron domains is maximized. So that's how we end up with these shapes. Balloons actually kind of fill that. So electron domain geometries, for example, if we have 6 balloons, we have an octahedral balloon geometry. But if we have 6 electron domains, then we'll also most likely have an octahedral electron domain geometry. Now, that doesn't mean that we have an octahedral molecular geometry, because the molecular geometry requires there to be atoms there. But we may well have an octahedral electron domain geometry. 5 balloons then, trigonal bipyramidal electron domain geometry. 4 tetrahedral, 3 trigonal planar, 2 is linear. So molecular geometries for 5 electron pairs. So these are all based on the trigonal bipyramidal shape. So we talked about before this AX5, this PF5, which is down here in the bottom left. Here we have 5 bond pairs and no lone pairs, PF5. So all of everything on this page is based on the trigonal bipyramidal shape. So this is the electron pair domain. So we're talking about 5 electron pairs, but that's not the same as 5 bonds, not the same as 5 bonding interactions. So in the case of this one, PF5, we do have 5 bonds, we have no lone pairs, and we have a trigonal bipyramidal molecular geometry. Then if we have here, for example, 4 bond pairs and 1 lone pair, such as SF4, I talked a little bit about that earlier whenever we looked at the structures which have an extended octet. They have more than 8 electrons in their valence. SF4 was a classic example. It has this seesaw shape. So it has 4 bonds and 1 lone pair. So its molecular geometry is the seesaw shape, this Mg, whereas it still has the same electron domain geometry. It still has this trigonal bipyramidal electron domain geometry. You can see it here in the polygon. So whenever we had a PF5, we had all of the lines were thick solid lines, and that indicated 5 solid lines, and that indicated 5 bonds, each one from phosphorus to fluorine. Now, however, we have sulfur in the center, but this dashed line indicates that we now have 1 lone pair, which is here, which corresponds to here, and then we have 4 bond pairs, which are the filled solid lines. Then here's another one, ClF3. That's a T-shaped geometry. So its electron domain geometry is still trigonal bipyramidal, as shown by this polygon. But now we have 2 lone pairs, as indicated by these dashed lines. And then we have 3 solid lines, which give the T shape. You kind of see it's like a little bit like a T. Here's the top of the T, and here's the bottom part, the part that goes down. Just rotated on its side, so rotated here, kind of like a T shape. Then there's 3 bond pairs and 2 lone pairs. And then here we have a linear structure, a linear molecular geometry, but still with that trigonal bipyramidal electron pair geometry. Only this time we only have 2 bond pairs and we have 3 lone pairs. Okay, so an example here, PCl5, phosphorus has 5 valence electrons, and each chlorine atom needs 1 electron to complete the octet. So it gets 1 electron from the phosphorus. So 1 electron from the phosphorus in each bond. And so it then is able to form this trigonal bipyramidal structure. So both the molecular geometry and the electron pair geometry are trigonal bipyramidal. The molecular geometry only considers the actual bonds of the molecule when determining what geometry it adopts, whereas the electron pair geometry looks at both the lone pairs and the bonding pair electron domains. So it looks at where all of the electrons are around the central atom. Then looking in more detail at SF4, so sulfur has 6 valence electrons. Each fluorine atom needs 1 electron to complete the octet. Because of its ability to sort of extend its valence, it's able to share 4 of its valence electrons with the 4 fluorines that need 1 electron. So that's forming 4 sulfur fluorine bonds. And then it has 2 electrons left over, which form the lone pair, which is why we have this so-called seesaw shape. The reason why it's called a seesaw is because if you rotate this on its side, you end up with a structure that looks a little bit like this, which if you sort of put 2 people on the end, kind of looks like a seesaw. It's a terrible drawing, but hopefully you get the idea. So they're supposed to be on the seesaw. But if you can kind of imagine a children's playground, then we have a seesaw. That's why it's called a seesaw. Here are the legs of the seesaw, and this is sort of like the beam or the bar of the seesaw. So the molecular geometry here is seesaw because it only takes into account the bonds, whereas the electron-pair geometry, it is trigonal bipyramidal still because it considers all of the electron domains. So we have 4 bonding domains, and then we have 1 lone pair domain. So it is still going to be, what do you call this? Still going to be trigonal bipyramidal for its electron-pair geometry. Okay, so then molecular geometries for 6 electron pairs. So these are all based on the 8-sided octahedron. So here we have the octahedron. So it's a square with something like this. Okay, I made that way worse than it was. All right. So here's the octahedron. Here, if we place the atoms on each one of the corners or the vertices of the polygon, we have what's called an octahedron. We have a central atom here in the middle, and then we have 6 bond pairs or 6 electron domain positions. So octahedral shapes such as SF6, remember sulfur has 6 valence electrons, and so it can extend its valence and have a structure such as SF6. So it has 6 bond pairs, no lone pairs. So we have an octahedral molecular geometry and an octahedral electron pair geometry. Then BRF5, we have 5 bond pairs and 1 lone pair. So here we have the 5 bonding pairs and 1 lone pair. We have what's called a square pyramidal molecular geometry, but the electron pair geometry is still octahedral because the lone pair, it occupies this 6th position, this corner at the bottom, and that gives us the electron pair octahedral geometry. Then in the case of xenon tetrafluoride, we have 4 bond pairs and 2 lone pairs. So here we have 1, 2, 3, a lone pair above and below. And so this is our square planar structure. All of the bond pairs are here shown in this solid line, and we have the lone pairs above and below this plane. It's called planar because these bonding pairs kind of sit all in the same 2-dimensional plane. So that's the molecular geometry, but because of the lone pairs being above and below, we still have this octahedral electron pair geometry. So compounds with 5 or 6 pairs around the central atom. So this is looking at this in more detail. So this is the case where we have an octahedral molecular geometry and an octahedral electron pair or electron domain geometry. So hopefully you're starting to see the difference between what an electron domain geometry is and what a molecular geometry is. A molecular geometry only considers the actual bonds whenever it's giving its descriptor, but in the case of the electron domain geometry, it also considers the lone pairs. Because where the lone pairs are is important because as you can see here, they still take up space. They're still having an effect and causing the other atoms to arrange in a sort of square planar manner in this one, because if they didn't, that's 4 bond pairs. If we remember back, methane had 4 bond pairs, so why doesn't this form a tetrahedral geometry? And it's because of this electron pair geometry, the fact that we still need to fit those lone pairs around the central atom. If the lone pairs just didn't disappear. In methane CH4, it doesn't have a lone pair, and so it can form a tetrahedral geometry. So compounds with 5 or 6 pairs around the central atom, so this is an octahedron. So this is SF6. You can see here it has 6 bond. So SF, SF, so it's got 6 of those SF bonds. There are no lone pairs in this instance. So the molecular geometry is octahedral and the electron domain geometry is octahedral. So both the molecular geometry and the electron domain geometry, EDG, they're both an octahedron or octahedral. We have 6 electron pairs. We distribute them at 90 degrees from each other, which kind of like minimizes that repulsion as much as possible. Predicting molecular or ion shape. So the first thing we do is we write out the Lewis structure. That gives us an idea of the connectivity of the molecule without sort of complicate things too much yet. Then we count the number of electron domains around the central atom to determine the arrangement, minimizing repulsion. So here we start to consider the lone pairs and the bond pairs. Then we describe the molecular geometry in terms of arrangement of the bonding domains. And double and triple bonds are counted as one domain for determining molecular shape. So remember that when predicting shapes of molecules with double or triple bonds, the VSEPR model, multiple bonds count as one effective electron pair. So say we have a carbon here, that's with 1 bond, don't worry about the others yet. That's 1 electron domain. If we have a carbon with a double bond, that's still only 1 electron domain. This is still only 1 electron domain. Because the electron domain sort of only considers where the electrons are, not really how many there are. Influence of lone pairs around an atom. So lone pairs require more room than bonding pairs and tend to compress the angles between the bonding pairs. So they sort of push out more. This is because if we think about it, whenever an electron pair is involved in bonding, such as a carbon-carbon bond, it's confined more or less to that area between the 2 atoms. Now, if we think back to our ammonia, our NH3, if we recall, ammonia is in group 5, or sorry, nitrogen is in group 5, and it had a lone pair here. Now, that lone pair, it's not confined to sort of a small domain between 2 atoms. And so it can actually form a much larger, much more space, because it's not really doing anything yet. I mean, it may well do something in the future, but if we're just considering the molecule or the compound on its own with nothing else around it, then the lone pair doesn't really have much to do. So it kind of just fills as much space as it can. And so it's this space, filling of space, which causes it to compress the other bond angles down. And so it ends up creating what the ammonia structure is more like, which is all of the hydrogen sort of pointing in one direction, sort of pointing down in this case, because the lone pair exerts its influence and sort of takes up a lot of space. So lone pairs require more room than bonding pairs and tend to compress the angles between the bonding pairs. So the influence of lone pairs on the so the influence of lone pairs on the molecular geometry. So here we're looking at tetrahedral electron pair geometries. Actually, here's ammonia, which we were just talking about. All 3 of these, much like our previous examples with trigonal, bipyramidal, and octahedral, all three of these have the same electron pair geometry. So they all have a tetrahedral electron pair geometry. So methane, or CH4, it has 4 bond pairs and no lone pairs. And so it has a tetrahedral electron pair geometry and a tetrahedral molecular geometry. The sort of angle between each one of these bond pairs is going to be the same because the bond pairs repel each other by the same amount because they have the same construction. They're all CH bonds. Then in the case of ammonia, what happens is we still have this tetrahedral electron pair geometry, but now we have a trigonal pyramidal molecular geometry. What we see is that this causes a compression of the bond angles. The hydrogens all sort of point in the same direction. And from the Lewis structure, they're no longer pointing in 3 different directions, and they're all kind of pointing down. So you can see that ammonia here is really just methane, but if we remove this one of the carbon hydrogen bonds. So now we have NH, 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 3 NH bonds, 3 bond pairs, 1 lone pair here at the top. The lone pair takes up more space, so it pushes the other bond pairs together. It increases their repulsion, obviously, because they're getting closer together, but because the lone pair repulsion is stronger than the bond pair repulsion, we see a compression of this bond angle, and so a reduction of that bond angle. And so that bond angle becomes 107.5, so it's a reduction of about 2 degrees, and so that's not an insignificant amount. And then water as well. Water has a tetrahedral electron pair geometry, but it now has 2 lone pairs. So here's a lone pair 1 and 2, and so it has a bent structure where the OH bonds are quite close together, 104.5 degrees. So you can see that compression has become even greater. So going from methane to ammonia, we went down 2 degrees, but for ammonia to water, we went down by 3 degrees. And so the reason for this is because the lone pair repulsion is even greater than the lone pair bond pair repulsion. So these 2 lone pairs are repelling each other, and then this lone pair is repelling the bond pair. And then the bond pair repulsion is happening like this. So we have 2 bond pairs, 2 lone pairs. So the bond angles here, methane has 109.5 degrees bond angle, 0 lone pairs, tetrahedral molecular geometry. Ammonia, 107.5 degree bond angle, 1 lone pair, trigonal bipyramidal, and water, 104.5 degrees, 2 lone pairs, and it has the bent molecular geometry. So now we want to kind of draw the Lewis structure of phosphorus pentachloride. So phosphorus is in group 5A, chlorine is in group 7A. So we have 5 valence electrons from phosphorus, and phosphorus pentachloride is P for 1 phosphorus, penta, we recall is 5, so we have Cl5. Okay, so then we have 5 times 7 is 35 electrons from chlorine. So we place the least electronegative in the center, so it's going to be phosphorus. And then we place the chlorines around it. So 1, 2, 3, 4, 5. And this is the Lewis structure, so we don't actually need to sort of show the molecular geometry just yet. We have here a total of 40 electrons. Then we have 5 bonds, so 40 minus 10, so that's 2 electrons per bond pair. It gives us 30 electrons. So then we distribute the lone pairs. So on each of the chlorines, there will be 6. There are thankfully 5 chlorines, so 6 each. 5 times 30 gives us, or sorry, 5 times 6 gives us 30. And that should be 2 electrons. Okay. And so we find out that that is indeed correct. We do have PCl 5 has, well, this is the molecular geometry as well, more or less. So we could draw this out with like those kind of wedges. I was better at doing that. And this one could be like that, the filled in wedge, which means it's coming out of the page. And that would give us the molecular geometry as well. I tried to draw a 3D picture of phosphorus pentachloride. So phosphorus in the middle, chlorine at the top, chlorine at the bottom, because it's got a trigonal bipyramidal structure, because it's got 5 electron domains. And like so. So this dashed wedge here, that means it's going into the page, and this filled in wedge means it's coming out of the page. So draw the PCl4 plus ion. So this means that we have lost a chloride. So if we go from PCl5, that's the term, hang on, make that easier to read. PCl5, and we're going to PCl4 plus. We have lost a chloride. So likely, like, I don't know, like, so most likely it's going to be a tetrahedral structure. Because the reason why I'm saying that is it not only has 4 electron domains. Like in the previous cases where we've kept the same geometry, we've had a lone pair. But if we think about the Lewis structure here, so now we have phosphorus is still in group 5, 5A. Then we have 4 chlorines and 7A. So that's 7 electrons. So we have, from these, we have, what's that, 5 plus 7 times 4 is 28. So we have 33 electrons, minus 1, because we've got the positive charge, which gives us 32 electrons. We then form the phosphorus in the middle with 4 bonds around it, so that's minus 8. So that gives us what, 24 electrons, and so those go on each of the chlorine. So there's 6 on each chlorine. There are 4 of those, so 4 times 6 is again conveniently 24. And so the structure is showing that we have only 4 electron domains on the phosphorus, which are the 4 bond pairs. So most likely it's going to be a tetrahedral structure. So there's the Lewis structure there. Again, I'll draw it again. Because it's got 4 electron domains. Which are the bond pairs. PCl 6 minus, but we're kind of going to be doing the same thing. So phosphorus group 5, chlorine group 7A, there's 6 of them. So 5, 6 times 7 is 42. plus an electron for the -1 charge. So that gives us 48. Draw the phosphorus in the middle. 1, 2, 3, 5, 6. Okay, so that's 1, 2, 3, 4, 5, 6 bonds. So 6 times 2 is -12. So the bond pair, so it leaves us with 36 electrons. 6 on each chlorine again. There are 6 chlorines, which conveniently takes care of our extra 36 electrons. So now we have this, these brackets indicate that it is a complex ion, which means the negative charge is spread across the entire molecule. So there we go. Don't forget your negative charge. Draw the 3D picture. Most likely we have phosphorus, chlorine, 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 going out of the page. That's a really big wedge. So chlorine, chlorine. So it has an octahedral geometry. Xenon tetrafluoride then. So xenon is in group 8. Fluorine is in group 7 still. So let's see. The 4 of those, because it's tetrafluoride, XeF4. So remember that, I guess we'll go back to module 2. Tetra means that we have 4. So we have 4 fluorines. So 4 times 7, 28. Xenon is 8 in its valence, gives us 36. So we have xenon, put fluorines in. So all right, so we have 4 bond pairs, so that's 36 minus 8 gives 28. Okay, then we distribute the remaining electrons as lone pairs. So fluorine here, each one gets 6. So in this instance, we're going to have leftover electrons, in fact. And so if we count up the number that are as lone pairs on fluorine, that's 6 on each. 6 times 4 is 24. That leaves us with 4 electrons remaining. So those 4 electrons become lone pairs on the xenon. So now the xenon has 6 electron domains, as opposed to before we just had electron domains which were the bond pairs. Now we in fact have electron domains which are lone pairs on the central atom, which is going to affect our molecular geometry. So there we go. So there's the xenon tetrafluoride Lewis structure. So the 3D picture of xenon tetrafluoride is going to be based on an octahedra again. So it's kind of hard to draw on this. So most likely the structure is going to be, the molecular geometry is going to be square planar. But the electron domain geometry, because there's 6 electron domains, will of course be octahedral. Okay, and we'll leave it there because I'll talk about electronegativity next time. So we'll end there with the trying to rationalize how the Lewis structures can help us to get the 3D molecular geometries based on, we drew out the list structures like so, and then we got the molecular geometry from that based on what we had learned in the previous part. So any questions?